Good morning, students, or good day, I should say. Anyway, if it seems like that last video ended abruptly, that's because I was over the time limit and I had to cut it short, and now we'll move on from where we were, which was about to talk about the stem and leaf plots. Sometimes you see it as just stem plot, but really appropriately it should be called stem and leaf. So the idea here is every single data point is shown, and what you see is on the left here you see this stem, and that's basically showing that you have numbers less than 10, then 10 or more, 20, 30, 40, 50, 60, and 70, and then the number shown on the right is the second digit of the numbers. So this is a 4, a 6, a 12, a 14, and an 18, down to the largest number, which is 72. So this allows us to start to see the shape of the distribution while maintaining the numbers, original numbers of the data. It's really a great idea. The person that developed this was a very creative person, and I've used this a lot of times when I'm in a class or something and I'm not going to put the data in the computer. I can just compile it on a stem and leaf diagram and start to make some sense of the data. The one on the right here was done a little differently in that these are the same, and that these are numbers between 10 and 20, but there's two stems here, one for those that are under 15 and one for those that are above 15 and below 20. You see 21, 21, 23, 28, and 29, so they made these into 5 units of 5 to get a little bit more definition on this, because it doesn't have as big a range as the one on the left. So this is a tool to be used, and it's quite flexible. This one is also available in StatCrunch, as we shall see here. And this is an example from everyone that was at a birthday party, and shows all the ages, and they were compiled into a stem and leaf plot. You see that we've got some children that were under 10, starting with a couple of 1-year-olds all the way up to a 66-year-old person that was at this birthday party. So this is something you could practice on. If you were so ambitious, you could take this data and put it on a stem and leaf. But it's already been done here for you, as long as you understand what this plot is doing. And again, this one is available in StatCrunch. All right. This was another example, wait times at Splash Mountain. Recorded, and how long do people have to wait, and there you see it. Some people didn't even have to wait at all, and you see that this particular stem and leaf plot, there's a lot of data here, so it was put in, this is 100 observations, so it was put in units of 5, like we have talked about on the previous chart, and there you see it. And you can start to see the shape, that there's maybe multi-modes when there's not much of a line, and then you start to get bigger and bigger lines out there. I would hate to wait 70 minutes, right? But you've probably experienced something like that if you've been to Disneyland. All right, let's move on, and we're going to talk about distribution shapes. This is kind of, we introduced this with that socks idea. Now we're going to talk about shape a little bit more specifically. We're going to talk about symmetric versus skewed distributions. How many mounds or peaks are there on the distribution, and is there indication of any unusual data points? So I like this chart that illustrates, it doesn't illustrate every distribution, but it illustrates the shapes that we're mostly interested in describing. So the one on the top left there, you see that it's that looks like a single mound, or a single mode, as we call it. Mode is the most frequently occurring value, and so if you see a single peak, that means that right in the middle there is the most frequently occurring value, or range of values anyway. And you see that on this that one, the tails go off at about the same magnitude in both directions. So that's symmetrical, and it's got a single peak. The one on the upper right, that's called the uniform distribution. Meaning that all the things that are occurring are equally likely. In the airplane example, the bomber pilots, planes that we talked about, and Abraham Wald deducing that there was one area where there were significantly less bullet holes than any other. Well, that was the engines, because those engines that got hit significantly didn't come back. So we would have expected a uniform distribution in that particular case, and the fact that they didn't get it was a signal to Wald that something was going on. If you roll a die and record the numbers 1 through 6, you should expect to see this kind of a distribution. They should all be equally appearing in equal frequencies. Okay, the one on the lower, you see a skewed distribution on the lower left hand. One is called skewed left and the other is called skewed right. I've got another chart on that just coming up in a minute. How do you remember which is left and which is right? The way to remember is that the one with the long tail on it is the direction we're talking about. So you see skewed right data in a lot of places where you're counting things up. And then the one on the bottom right, that's kind of important. If you see more than one peak in your data, there's a good chance that something's going on there that's causing those 2 peaks, and so that would be something to investigate. See if you can figure out what's causing those 2 peaks. I've had that happen many times, and the investigation usually ends up being interesting. All of these distributions on this chart, the first characteristic shape, they're all symmetric. It's just that they all are quite different from one another. So the idea of symmetry is it's the same going in both directions, to the left side and the right side, and you see that in all of these distributions. So symmetry is one characteristic that we're interested in. Here are a couple of distributions that are not symmetric, so we call them skewed. And so this mnemonic can help us remember when we say skewed right or skewed left, that means skied right or skied left, meaning that you could ski down the less steep side, if you will, and that would show you the direction. So that distribution on the left there, we call that skewed right, and the one on the right we call it skewed left. It's the direction of the long tail is the way to remember which is which. Okay, this is a unimodal distribution. By unimodal, mean it has one peak, a single peak, and you hear that the most famous distribution that we will talk about in this class, or the most well-known, is called the normal distribution, and it is a unimodal distribution, and pretty much looks like the one that we're seeing right here. It's got a single peak, and it's symmetric, tails going off in both directions. And when we have more than one peak, we would say, like if we had 2 peaks, we'd say it's bimodal, meaning that there are 2 frequently occurring values. Now, a mode means a peak, basically. So that's why we use this bimodal and multimodal designation. So if you see something that it doesn't tail off smoothly in one or both directions, then you'd say, well, that's bimodal or multimodal, depending on how many peaks that you see there, or mounds as we're calling it here on the chart. So they can be different heights, so you still think of those as modes. Technically speaking, the mode is the most frequently occurring value, but the idea here is that we're seeing more than one distribution. So if you've got a bimodal distribution, as it says in the middle there, it means that you probably have 2 groups in your data, and if you can separate those groups, then you might get a better looking distribution, one that's more symmetric and unimodal and so on. So for example, if you put men's and women's heights together in a data set and graph the data, it would almost certainly be bimodal. But if you separate men and women, then you'll see a more typical distribution. And so that might be the best way to treat that kind of data if you understand what's causing the bimodality. Afternoon versus evening sales at a restaurant. If that restaurant tends to be more of a lunch or more of a dinner site, then you're going to see bimodal. Of course, you're going to see the peaks in the afternoon, right at dinner time and right at lunchtime, if you're plotting the data for throughout the day. Okay, this is an interesting exercise here to think about what kind of shapes you would probably see in this kind of data. So GPA of college students, well, that's an interesting one because it can't go above 4.0 or 5.0 depending on where you're at. 4.0 I believe here at this university. So, but you could get a long tail on the low side, so we'd say that's skewed right. It's going to be a lot of high grades, but not many low. But you'd have a decreasing amount going off to the right. SAT scores, they tend to be symmetric. and mound shape. So there is a middle value there where people tend to fall, but you're going to have people that excel and get above that, and some that don't do so well, and they're going to be on the low end. So in fact, those scores are designed to be somewhat unimodal and symmetric. The last digit of social security numbers for a sample of students, well, those should be a uniform distribution, right? Symmetric, uniform. They should all occur about the same amount, just like our the bullet hole data should have occurred at equal amounts, and it didn't. In this case, you'd expect a uniform distribution. And income of USA residents, again, skewed right, that there's a long tail on the high side. You put Bill Gates in there with everybody else, or the Jeff Bezos, the owner of Amazon, their numbers are really big, so you got a long tail on the high side. Obviously you can't go below 0, so you got a short tail on the low side, so that distribution, you'd expect it to be skewed right. Also, you should be aware, and this is another element of shape, that extreme large or small values, we tend to call those by the term outlier. Outlier means it's out there by itself, or you could have two outliers where you've got two numbers out there. They don't fit the pattern of the rest of the data. And as our data analysis purpose is to try to understand the underlying structure of the data, then that's part of the structure. So we've got maybe a nice symmetric distribution or a little bit of a skewed distribution with an outlier, and so that outlier is important to us because it's telling us something unusual happened out there. There's no precise definition of an outlier, as it says on that third burger dot. But there are some criteria. We'll see when we get to the box plots that it uses a criteria for designating outliers that is very helpful. So we'll see that. But if it looks to the eye like something unusual is going on, as it clearly does in this case, the weight on that thing is way above anything else that we see, then we would say that's an outlier, and we might remove it from the data set and say we have this distribution with an outlier at 1,200 pounds, and we're investigating how or why that happened. These occur all the time. One way that they can occur is if you have an error, and if you have an error, then you can just correct the data. I call that an out and out liar, right? It's the data's lying, it wasn't real. But in other cases, that observation is very correct and very real. The question is, why was it so different? So when you see those kind of things, report the values, realize it could be an error, and we should figure that out. And genuine outliers are unusually interesting data values. They usually are calling for an investigation to figure out what happened. I don't need to go into the entire history on this, but there are many inventions and many unique things that were outliers, and somebody looked into it and said, well, why did this happen? One of them is, you might be familiar with Teflon. Teflon was an outlier. Something, they were trying to make something or create something, and this was like, what is this stuff? And they investigated, found out it had all these non-stick properties. And so that was an interesting discovery. The data from the goals, you see that we have the women's goal scoring data from Division 3, and this one we haven't seen before. The data on the right is for men scoring, and what you see there is a little bit of a skewed distribution on the women's side, and the men's side it's a little bit more symmetric, and it looks like the typical values in the center, which is what this slide is about, right, is a little bit higher for the women than it is for the men. So typical score, number of goals was 16 for the women, 13 for the men. So it appears a little bit that there's the typical value is a little bit bigger for the women than it is for the men from this. One thing to be aware of, keep in mind the scales are different on those two graphs, right? So it's very clear that there's more spread on the women's side than there is on the men's. And also you see there's a little bit of a difference on the average. So we would be interested in both the center and the spread, and that's what this next graph is pointing out. Now, one way to show that spread even more effectively than what's shown here is to put them on the same scale.